Hi friends, welcome back to my channel on statistics. If you are seeing my videos first time, then do subscribe. Don't forget about subscribe. In this video, I will mainly explain about basic definition with examples of unbiasedness, consistency, efficiency, and sufficiency. Okay, these four are the ideal ideal properties of estimator. Means for becoming an ideal data set best estimator, then the data set must be satisfy these four properties: unbiasedness, consistency, and sufficiency. If you see this full video, then you can clear about basics of unbiasedness, consistency, efficiency, and sufficiency. From the next lecture onwards, I make clear about unbiasedness. From the next lecture onwards, consistency also. In unbiasedness, we have lot of results related to uniformly minimum variance, locally minimum variance, mean square error, and Kramer-Rao lower bound. All things we discussed in next video, but in this video I will give you a quick overview about unbiasedness, consistency, all estimators. Okay, now go to the topic. See, this is the unbiasedness. An estimator Tn is said to be unbiased estimator for of theta if the expected value of Tn means function of sample values. Okay, function of sample values is equal to this is the expression of unbiasedness estimator. See, expected value of sample statistics means any sample drawn equal to the population parameter. It is called unbiasedness. If it is not equal to tau of theta, then we can say this bias estimator or bias. Bias will be negative or positive, all things. Okay. In short, the estimator is unbiased if the mean of the sampling distribution of Tn, mean means expected value of, I'm telling a simple example, x bar equal to mu means here x bar is the unbiased estimator for mu. This is the conclusion. Okay, like this. Also, the difference between, see, if we need bias, here bias is 0 plus bias is 0. If we need to calculate bias value, then expected value of Tn minus tau of theta become the biased formula for bias will be negative or positive will be positive, then tau of theta is less than expected value of Tn, and negative if tau of theta is greater than expected value. Now I can see some examples. Okay, my first example is related to the binomial distribution. We all know that binomial distribution have two parameters with n comma p. Okay, here clear. Here x follows binomial distribution with n comma p. Now I want to find the unbiased estimator for p. Here I am taking now parameter. Here I need unbiased estimator for p. For finding unbiased estimator of p, I am taking x bar expected value of expected value of x bar. How we can calculate expected value of x bar means summation 1 into n upon n into summation I equal to 1 to n xi. Here n times 1 by n into n upon. Okay, finally you got p. See, this is so mean is the unbiased estimator for p. If you calculate expected value of x by n, expected value of x by n also unbiased estimator for p, means there is infinite number of unbiased estimator exist. Unbiased estimators are not unique. We can discuss these all properties in next video. I am just telling. Okay, if you take Poisson distribution, for example, my x follows Poisson lambda, then what is unbiased estimator for lambda means you can just take x bar. Expected value of x bar is what? Lambda. N lambda divides n lambda. Finally, you got lambda. This is unbiased estimator for lambda. You can take another example also. There is infinite number of unbiased estimators will exist. If it has a convex set and it will be one-to-one function, all things you can discuss from next video. In this video, I will give quick. For continuous distributions, I am take I am taking that. This is my third example. Exponential distribution. X follows exponential theta. Here my PDF is 1 upon theta into e power minus x by theta. This is my PDF of exponential distribution. Here mean is theta, then x bar becomes the unbiased estimator of theta. Okay. If you take normal distribution, x follows normal distribution with mean mu and variance sigma square, then what is unbiased estimator of mu means x bar, that is clear. But what is unbiased estimator of sigma square is not equal to s square, means here population variance is not unbiased estimator, this is biased estimator. When s square equal to 1 divides, when you check sample variance unbiased estimator, then it will become unbiased estimator. But population variance is not unbiased estimator, sample variance is unbiased estimator. Okay, that's x bar. Okay, these all are some examples. Also from the next video we can clear about unbiasedness. Okay, now we can see about consistency. Okay, consistency. An estimator Tn calculated from the n samples varied is said to be a consistent estimator of a parameter theta if for any individual small positive quantity epsilon and a small positive number mu, there exists a capital N such that following inequality holds. This when you observe this, what is this inequality? Convergence in probability. Expect like probability of x bar minus mu is less than epsilon, like this. This is a convergence in probability. When you can take example, probability of x bar is an sample statistic, then mu is the parameter, then it will be satisfied convergence in probability condition, then we can say that consistent estimator. There is invariance property also there for consistent estimator. What is invariance property means? If sample values are unbiased, then variance of Tn tends to 0 when n tends to infinity. That time also we say that it is unbiased estimator. Okay, we observe this also. Hence Tn converges in probability to tau of theta or stochastically converging into tau of theta. The above definition is known as simple consistency. In short, Tn is said to be n consistent estimator. This is definition for convergence in probability. Here you can apply one more result also there. That results also, that is this. What invariance property? A lot of properties are there. We can discuss it in consistency lecture. Consistency is a limiting property of an estimators and it revolves the behavior of estimator Tn. This is that property. When x bar and x bar by n minus 1 all consistent estimators of population, mean and the selection either of them. These all things also we can discuss it. Okay, now we can move to the examples. Okay, now we seen that expected value of x by n is unbiased estimator for p in unbiasedness examples. Now we need to find the consistent. For finding consisting estimator for p, here x by n is what? Unbiased. Now we need for checking consistency when variance of Tn means variance of test statistic equal to 0 when n tends to infinity. If you find variance, then n tends to infinity, it automatically goes to 0. You can take that examples also. Expected value of x bar in Poisson distribution. Same examples I am taking. Expected value of x bar. When you can solve, when you find variance, then automatically n tends to infinity means n tends to 0. Here what you get? Lambda by n. For variance of x bar you get lambda by n. Lambda n means equal to 0 when n tends to infinity. Okay, this type of examples. You can take exponential distribution, normal distribution, all distributions, every unbiased estimate. There is one property is also there. Asymptotically unbiased means when n tends limiting distribution n tends to infinity, then it will be going to the parameter mu or sigma square lambda. Then we say that is also unbiased, asymptotically unbiased estimator, but it is not fully unbiased estimator. Now we can see the efficiency. This is third property of unbiasedness. Sorry, estimator. This is third property. An unbiased estimator Tn is said to be an efficient than any other estimator Tn star for tau of theta if and only if this condition, which test statistic has less variance, then we say that it is efficient. If this is less variance, then we can say that it is efficient. If it has this less variance, then we can say that it is efficient estimator. This is the relative efficiency. Kramer gives this theorem we can discuss in literature about Kramer-Rao theorem. Now we can move to some examples of efficient estimator. For example, my xi is IID random variables following Poisson lambda. We all know that mean and variance is equal in Poisson distribution. Now I want to check, this is my one example, tx1. This is my test statistic 1 is what? X1, only x1. Okay, understand? Then I am taking tx2 also. tx2. My test statistic 2 is x1 plus x2 divided by. This is also what? Just like mean. This is also mean. Okay, we can observe this also. x2 divides 2. This is another estimator also, that is tau of x3. What is tau of x3? 2x1 plus x2. See, I drawn three statistics from the exponential distribution x1 plus x2 divides 2, 2x1 plus x2 divides 3. Now I want to check if you check unbiasedness, here what you get? Lambda. This is unbiased for Poisson for lambda. This is unbiased for lambda. This is what? This is also unbiased for lambda. Here 2 lambda plus lambda, 3 lambda divided by 3, all are unbiasedness. And if you check efficiency, if you find variance of this, you get lambda. Okay, if you find efficiency of test 2, you get lambda by 2. Okay, if you find variance of third estimator, you got 5 by 9 lambda. How we got this? We all know that variance of ax is a square. Variance of ax is a square. Variance of x. Here when you here independent XIRs IID random samples means here independence, then covariance 0. Here 2 square is 4 plus 1 is 5 upon 9. If you can check the efficiency estimator which has a less variance, by observing we can say that 5 by 9 has a less variance. T3 means third statistic as best efficient estimator compared to the T2 also, T1 also. So T3 is the most efficient estimator. From the in efficiency class we can discuss uniformly minimum, locally minimum, all things also we can discuss in. Now we can stop this efficiency. Now we can go to the sufficiency. This is most important and confusing estimator property. See, an estimator Tn is said to be sufficient for T of theta. This is definition 1. It provides the all information contained in the sample about the parametric function T of T. If you take any statistic from the population, then you test unbiasedness, consistency, efficiency, then sufficiency also most important. Sufficiency gives the most useful information from the data set. So sufficiency is most important. See, if we have a random sample, means sample x1 from a density of a statistic, this is my sample values, function of sample values, which is conditionally and random variable into a single random variable, provides the much information as the random sample. Reverse that, probability distribution of characteristics of see, this is important. So the idea about that, now known as sufficient statistics, there is no need to knowing the sample values. You can understand what is this. Okay, there is one most important results there in sufficient statistics, that is Niemann factorization theorem. Niemann factorization theorem. Niemann factorization theorem. By assuming the Niemann factorization theorem, we can solve lot difficult derivations also shortly by using a likelihood function. We can discuss in this in examples. Now we can see this is a second definition. Sufficient for theta, then density if conditional distribution is independent of, when you find conditional distribution like probability of x equal to x given x equal to sample, here independent of theta will come, then we can say that it is sufficient distribution, otherwise we can say that not sufficient statistic. This is the definition 3. This is the most important result also, Niemann factorization theorem. This definition is known as Fisher-Niemann factorization theorem. The theorem can be stated as follows: let x1, x2 and so on xn be a random samples from a density of x and x statistics. Then you can find likelihood function, then you can divide like this, then you can divide our likelihood function into like this, then you can say that what this function of g values, you can say that it is an sufficient statistic. Now we can see the examples, you can clear about sufficient statistic. For example, I am taking binomial distribution. We all know that likelihood function of binomial distribution by binomial ncx p power x into q power n minus x. This is the PMF of binomial distribution. Now I want to find the likelihood function. When I am finding likelihood function, n into summation x, here summation for my equal to 1 to n, p into summation x q power, here summation, when you apply summation n square minus summation x. By observing, we can say that this is sufficient statistic. How we can say that this is, we all think we can say take it as the g of x function. Here hx function is into multiplied by 1. This is summation of xi goes to the sufficient statistics. Okay, if you see the Poisson distribution e power minus lambda means minus n lambda, lambda power summation x means summation xi, x factorial means here pi multiplication is there, pi I equal to 1 to n xi factorial. By observing, you can divide h of function and g of function. You can say that lambda power x is the sufficient statistics. In sufficient statistics, summation x is the sufficient statistics for the Poisson distribution. You can find exponential and normal distribution, all distributions also. You can see some details. There is lot of application is there in a sufficient statistics. We can discuss all things also in sufficient statistics. There is lot of use there in order statistics, nth large order statistics and nth small. Smaller statistics, larger statistics also we can discuss with uniform and exponential examples also, lot of results also there. This is the minimal sufficient statistics. The idea of a sufficient statistic is to condense the data to form that provides the maximum information. Yes, by using the sufficient condition we get maximum information. Hence the sufficient statistic S will be termed as minimal sufficient statistics if the statistics for the sample x1, x2 and so on xn cannot be condensed more beyond S without sacrificing the sufficiency. When you can see the examples of minimal sufficient statistic, then you can understand. This video full details about, I think after 3 videos I will upload sufficiency statistics. Okay, this is the complete statistics. This is also I upload after 3 videos. See, completeness, auxiliary, sufficiency. They have completeness, sufficiency, completeness, auxiliary. These all come from one video. when you understand sufficiency, then you can understand completeness. When you understand completeness, then you can understand auxiliary. Auxiliary is simple. Completeness and sufficiency is some derivation part is there, some thinking part also there. This is the complete definition. Let f x of theta be a parametric family of a univariate or multivariate distribution depending on the vector of parameter theta, and h of x be any statistics independent of theta. Means here sufficient also useful. Expected value of hx equal to the integral. This is when expected value is equal to 0 for all theta, then we say that it is complete, otherwise not complete. Here we get lot of results also there. We can discuss lot of results also. From next video I start on unbiasedness, order statistics with examples, and I will discuss MCQ also from related to the unbiasedness. And my focus is on order statistics. From the next onwards we can move to the consistent estimator. Thank you for watching. If you have any queries, you can contact me by comment or mail or WhatsApp. Thank you.